Hi, this is Roger from Labs, and today part 4 of our long-running video series about the properties of AM magnetic antennas. Today we'll talk about the skin effect and the proximity effect and how to counteract their negative effects. But first of all, let's recap what we had as a result in our last part. We had our tank circuit consisting of a capacitor, usually a variable capacitor for tuning, in parallel to an inductor, usually a coil, which is also the reception antenna in AM magnetic antennas. And what we have learned was that the Q factor, which we want to optimize, which usually means to maximize it, depends strongly on the ohmic losses, or in general on the losses, but we can look upon as the capacitor, even if it's such a capacitor with air as a dielectric. The losses happen mostly in the coil, and the first effect are the ohmic losses. And we made some simulations and came to the conclusion, well, the DC resistance is of course important, but it cannot be all, because the calculated and simulated Q factor we got when we only take the ohmic resistance, the DC resistance of this example coil here into effect, which is around 2.2 ohms, then we get a much higher Q factor than the real coil has when it is measured. The calculated or simulated Q factor was 500, and the measured one is only slightly above 100 at a frequency of 1 megahertz. So we already had the conclusion there must be other detrimental effects that ruin your Q factor except for the DC ohmic resistance. And now let's take away the variable capacitor. And so the first thing that you already might have heard of that comes into play is the so-called skin effect. So here we see the English Wikipedia entry about the skin effect, and what we can see is that for alternating currents, the current only flows, or mainly flows, on the outer layer of, in this case, a round conductor, a round cable or wire, and the hue of the red color marks the current density. So you can see in the inside of the conductor there is absolutely or nearly no current flowing, and the current concentrates on a kind of sheet or layer, and that's why it's called the skin effect, on the outer surface of the conductor. And when the question now is, at which frequencies does this effect start? And here on the German Wikipedia entry about the skin effect, we have a nice table. And let's take a look at the upper end of the medium wave frequencies, radio band, at 1.6 megahertz. So the current is flowing only on a sheet of 42 micrometers thickness on the outside of a wire. That means if you have a wire 1 millimeter in diameter, then you have current only flowing on a very thin outer layer. And this even becomes worse when we go to the shortwave band. Let's take here a higher shortwave band, around 16 megahertz. There, the current only flows on a sheet 16 micrometers thick, And if we go to, let's say, FM radio here between 50 and 160 megahertz, then it's only a few micrometers. So now let's take a closer look at the consequences the SkinEffect has on the ohmic resistance of our conductor and how we can counteract them. Now we know from experience that for DC currents the ohmic resistance, except for the material, usually copper, is dependent on the total cross-sectional area, and so the DC resistance is proportional to 1 over the cross-sectional area. And for a circle, that's perhaps you might remember from school, it's pi divided by 4 times the diameter squared. So we can write that, or we can conclude that the DC resistance of a conductor goes down with 1 over d squared. That means if you double the diameter, you only get 1/4 the resistance, and if you triple it, you get 1/9 of the resistance, etc., etc. But what about the SkinEffect for AC currents? Now, we've just seen from Wikipedia that when the SkinEffect comes into play, sorry for my bad drawing skills, the current only flows in a kind of ring, outer ring or outer layer of our conductor, and the thickness of this layer or of this ring is called delta, the skin depth, and that is only frequency dependent. So now, that means that the current now flows proportional, or the DC resistance is now proportional to the surface, to the cross-sectional area of this ring. And now the area of a ring is just pi times the diameter times the thickness of the ring, and the thickness is in this case the skin depth delta. And that means for AC currents, now again the ohmic resistance goes down with the surface area, but this time of the ring and not of the whole circle, and that is only proportional to 1 over d. So that means we can counteract the SkinEffect if we just as in DC currents, if we enlarge the diameter, but now we have to enlarge it to very big diameters to get the same effect as with DC currents, because our resistance only decreases with 1 over d and not with 1 over d squared. And the second thing is, if we know that the inner part of our conductor just doesn't take part in the current flow, then we can leave it out, because we quickly get to diameters, even at medium wave frequencies, of several millimeters to get a low enough AC resistance. And so we can come to the idea, instead of using solid wire, which would become thick, stiff, heavy and expensive, we just use copper tubing, like in this square loop antenna. You can see down below are the 2 banana jacks, and this is a simple 4 millimeter copper tubing, and it has the same resistance as if I would take 4 millimeter thick wire, which I probably even wouldn't be able to bend without a vise. Or copper tubing is one thick wire, or after, I would say, 2 millimeters, you should go to copper tubing. That's not very elegant, but it is a way to counteract the detrimental effects of the skin effect. And just so there are only two things to remember. The skin effect raises the ohmic resistance, so it's an ohmic effect, if we can call it that way. And when the current only flows on the outer layer, on a very thin outer ring, then we either have to enlarge the diameter of a thick wire, or we go over to copper tubing of the same diameter. But of course there is another way to counteract it. So if we would divide our whole circular wire into very small single wires, which are all isolated against each other, and none of them is thicker than the skin depth, so it could even be as thick as double the skin depth. So if we split our wire into many small wires, then, and of course each wire has to be isolated against the others, so it must be single isolated like enameled copper wires, and the thickness of each wire should be equal or smaller than about 2 times the skin depth of the frequency that we are interested in. And that comes out to what's called litz-wire. So here's an example. Probably you won't be able to see it very good. It looks at the first time as if these are uninsulated bare copper wires, but it's not. If we would measure them with an ohmmeter, we would see that they are all isolated against each other, and perhaps you can see they are also twisted against each other. So there's a whole black magic science on how to construct so-called litz-wire. So that is perhaps the more elegant way to counteract this, because we can stay at the same diameter as with sufficient to give sufficiently low DC resistance. If we just split up our single wire into many isolated stranded litz wires. And I've made a separate video on how to tin litz wire. You have to be quite careful in the end, just that every single litz wire must be tinned. If you leave out only one wire, you will get really bad effects, because a single non-tinned litz wire at the end will act like a winding which gives you a short. I know it's not quite easy to understand. Just remember, it's very important that first of all, not a single wire breaks in your winding, and secondly, that at the end all the wires have to be tinned, not a single one has to be left out. So, the second way how to counteract the skin effect is litz-wire. And except for that it is, of course, more expensive than a solid wire, litz-wire has many advantages. You get away with the skin effect if you choose the right type. Here, for example, these are 90 single strands, each 0.1 millimeter thick, or I will show you another one. Here you can see there is no extra outer insulation, so we really have the PU insulated polyurethane insulated enameled copper wires and not an extra outer protection. I'll show you another one, which, sorry, I would have to magnify it really. This one you can already see has an outer silk layer here to protect it, because this one has very thin wires, all in all 16 wires, each 0.07 millimeters one, and we even have in our shop a litz-wires with, I think, 200 single strands times 0.02 millimeters. So you can go to quite high extremes with litz-wire. It's flexible, so much easier to wind a coil with litz-wire than with a single thick copper wire. And you of course can use a smaller total diameter, because if we would take recipe number 1 to use a very thick wire or copper tubing, we would get a much bigger diameter to give the same resistance as with litz-wire. So that's just a short introduction. 2 classical ways to counteract the effects, the detrimental skin effect. You don't have to remember or understand any of the formulas, because we will take a look at our Excel sheet where all the formulas are integrated, and you just can play around with it, and we will just in a second play around with our Excel sheet just to compare litz-wire with copper, with solid copper wire or copper tubing. So for a comparison between litz-wire and solid copper wire, we take again our example coil, which you have seen many times now. We just have to take a few measures. I've wound this medium wave coil with, as you can read, 170 microhenries inductance with exactly the litz-wire I showed you a second ago, with this 16 times 0.07 millimeter litz-wire. Now let's just measure the outside diameter, and we get something around 0.4 millimeters here as thickness. So this is also the distance from each winding to the next. And so we will compare it with a 0.4 millimeter solid copper wire. And what else do we have to know? Well, the problem in calculating a spiderweb coil is we don't have a constant diameter, because with each winding, that's why it's also called a spiral coil, the diameter enlarges. So we have to take the average diameter, and that comes out as, well, what shall we say? Let's say 50 millimeters. And the length on this time, we will later see that it's, we in our Excel sheet, we will call this the length of the winding, is around 12 millimeters. So let's remember this. We have 0.4 millimeter is the total thickness compared to a solid copper wire. We have 16 times 0.07 millimeter litz-wire. We have an average diameter of the winding of 50 millimeters, and we have what we call here the length of the winding. Imagine if you wind a solenoid winding, then what we just measured here as 12 millimeters would be in fact be the length of the winding. Here it doesn't look like the length, but also as a second diameter. but we call it here the length, that is 12 millimeter from, because the distance from first winding to last winding. So that shall be all. You can also calculate how many windings I've used here, at least approximately, by dividing the length through the average diameter. So these are around 30 windings, 30 turns. It are in fact a bit more. So that's what we all need to know. And now let's go to our Excel sheet. So here we are at our Excel calculator for AM magnetic antennas. I will make a separate video with many examples, just how to use it. I will explain only the basics here when I put in the values for our spiderweb or spiral coil. Now we take our standard frequency of 1 megahertz, or in other words 1000 kilohertz. We already know our coil has 170 microhenries of inductance, and to this belongs a capacity of 150 picofarad to give this resonant frequency of 1000 kilohertz or 1 megahertz. Don't care about the mu r here. This remains 1 for all materials except for ferrite rod antennas. Now we had as our winding diameter 50 millimeters. We had the length of the winding as 12 millimeters. Our winding, well, it's neither square nor circular, but circular comes nearer to what it looks like. It's of course a polygon, but it's nearly circular. And now the calculator gives us first the number of turns necessary to give 170 microhenries. Now I just told you that my coil has something, I would have to count it again, it's around 40 turns. So you see, this Excel sheet is not exact science. That is especially because spiderweb coils are notoriously difficult to calculate. But the accuracy is sufficient for our purpose, because now we are not interested in the total number of real turns, but on the detrimental effect of SkinEffect. And we do not start with the litz-wire. We start with the comparison. Thick wire of, so we have 1, the number of wires is 1. We take 0.4 millimeter as a comparison, and now we get some intermediate results which don't interest us. We still have to put in the specific resistance, but this is of course copper wire, so the right value is already here. And now we can see the DC resistance, if we would use truly thick copper wire, would be 1 ohms, which is quite okay, but the skin depth is only 66 micrometers. And the skin resistance is in fact 3.45 ohms. So the SkinEffect raises the DC resistance even of a relatively thick 0.4 millimeter wire, even at the relatively low frequency of 1 megahertz, even 3.3 times. In fact, to give a true comparison, we even would have to use 0.25 millimeter, and there we are already at 2.6 ohms DC resistance. That's quite near what we measured for our real coil, and 5.8 ohms as a skin resistance. So we take a look at, and here you can see the Q factor is ruined down to a value of only 30 just by the SkinEffect. And now let's compare this to the litz-wire I've used for my medium wave spiderweb coil with 16 strands, each 0.07 millimeters. Now the DC resistance is again in the range of 2.1, 2.2 ohms. Remember, we measured as DC resistance 2.2 ohms, so we already here, although the number of turns is not exactly like the real coil, we are quite near to the right result. And now the skin resistance is nearly the same, so we get a skin factor, how large the how much the DC resistance is raised is only 1.03. That means the skin resistance is nearly the same as the DC resistance, so we have neutralized the effect, the detrimental effect of the SkinEffect, just by using a single, a simple litz-wire with 16 strands, each 0.07 millimeters. And so we could be content with that, if that is all, but you perhaps have already spotted it. There is still another effect, and that is the proximity effect. And so we have to take one other effect into consideration, which is usually left out in most discussions because it's a little bit harder to understand and very hard to calculate. The formulas I've put in here are quite complex, and I only found one place to give a whole set of formulas, and even then there are still some approximations. So first of all, let's go back to Wikipedia and take a look at what the proximity effect is, what consequences it has also on the ohmic resistance, on raising the ohmic resistance, and what we can do to counteract it. We've seen at the SkinEffect that in a single wire the current only flows for AC frequencies, only flows on an outer layer, on a very thin layer. But now we usually have coils consisting of many turns, sometimes one turn touching the next turn. And there the magnetic fields that are generated inside each turn, they influence each other, and they are, you can imagine it as that they are pushing, one magnetic field pushes the magnetic field from the nearby wire further outside, and this kind of still amplifies the SkinEffect. So the current not only flows on a thin sheet or layer on the outside, it only flows on a small part of the layer. And you don't have to, the formulas for this are very complicated and not easy to find, and you always have to do some approximations. You don't have to care about that because it's all as good as possible integrated into our Excel sheet. And you just have to remember two things. First of all, if possible, do not use windings above a winding. So only use single windings and not windings above each other. And second, you can minimize the SkinEffect if you separate the single wires by ideally 6 times their diameter, which would mean the worst is if you have turns touching each other, and the proximity effect is minimized when you have a distance from turn to turn of at least 6 times the diameter. For example, if you have a wire 1 millimeter in diameter, then the next turn should be separated 6 millimeter from the before going turn. So now let's take a look at what our Excel sheet says with a few approximations. We still have our litz-wire with 16 single strands, each 0.07 millimeters in diameter. We already know that the DC and skin resistance are nearly the same, but now let's go a little bit downward. And now the proximity effect comes twice into play. First of all, as you can see here, between each turn, so each turn of our coil influences the next turn, and this gives an additional factor of 2.08 ohms. And now we have still another detrimental effect. Each strand of your litz-wire lies near to its neighbor, so this is called the internal proximity effect, and this enlarges our DC resistance. It's our ohmic resistance. It are still only ohmic effects. Skin effect and proximity effect just raise the ohmic resistance because the current no longer flows through the whole cross-sectional area evenly, but it's concentrated on a little part of the outer layer. And now we get a what I call the proximity resistance of our coil of approximately 7.35 ohms. Aha! Now we are finally way above the 2.2 ohms that we measured for DC resistance and which remains constant by the use of litz-wire due to the skin effect. And now we get a Q factor of approximately 144. Now we finally arrive near to what we really measured with this coil. It's somewhere measured between 100 and 150. So even though there are some approximations, we are now arriving at a Q factor that comes near to reality. And here we already can see, well, what use does it have if we minimize the skin effect, if the proximity effect in the end ruins all our efforts? So you have to balance between skin effect and proximity effect, and this only comes with, you can only optimize this by playing around with the Excel sheet or doing real experiments. And I will show you a very interesting graph just in a second. So this diagram is from a scientific investigation about the use of different litz-wires and taking into account really all the effects, and these are real measurements. And what is compared here is the red line is a single wire with the same diameter or effective cross-sectional area as a litz-wire. In this case, the litz-wire is 80 single litz-wires times 0.1 millimeter of each wire diameter. On the x-axis, we can see the frequency. Starting from 10 kilohertz, here we are at 100 kilohertz, this is 1 megahertz, and it stops at 5 megahertz. And the y-axis is the measured AC resistance. And now let's take a look. Of course, both curves start equally. They have the same resistance, and which here the skin and proximity effect don't at 10 kilohertz. They play no role, and so the lines are, or the resistance is equal to the DC resistance. But now let's go, for example, to 200 kilohertz, which would be the middle of the long wave AM radio range. Here we can see clearly the blue graph for litz-wire is much better, a factor of 2 around, than the single wire, because in the single wire the skin effect already comes into play. And here, through the use of litz-wire, the skin effect, you can see a very slight rise, but it's nearly does have no effect, and obviously the proximity effect at this frequency also doesn't have an effect. But when we go to the AM radio range, 1 megahertz is here, and the end of the AM medium wave radio range is here at around 1.5 megahertz. Here you can see the litz-wire, now due to the proximity effect, rises steeply in resistance, and the two lines cross each other at just by chance at the upper end of the AM radio range. So at 1.5 megahertz, it wouldn't matter if you use a litz-wire or a single wire with the same DC resistance and thereby the same effective diameter as when you would add up all the single litz-wires. And we can come to one conclusion. Here, it doesn't make sense to use litz-wire at frequencies, well, let's say above at least 2 megahertz, and you will not find any reasonable application where litz-wire is used above 2 megahertz. And there, depending on how your coil is really constructed and which wire you use, it could even be better to use single wire with a minimized proximity effect. For example, if you use a relatively thick wire and you place the turns with a great distance to each other, it could be better, even for AM radio, to use single wire than to use much more expensive litz-wire. So at the long wave range, it's clear litz-wire has a great advantage. At medium wave, it just depends. I would still say litz-wire is usually better if you use it the right way, but we will later see when in another video when I explain the use of our Excel sheet that there are places when single wire can, even in the medium wave range, be better than litz-wire. So let's finally put it all together. We have the two most important effects that raise your ohmic resistance, the skin effect and the proximity effect, and there are ways and measures to counteract them. We could, to counteract the skin effect, either use a very large diameter solid copper wire or hollow copper tubing when solid wire is no longer practical. Or we could use litz-wire, which is more elegant, a little bit more expensive, but flexible, has smaller total diameter, etc. But we always have to take into account the proximity effect. And how can we counteract it? First of all, never put winding on winding or turn on turn. So only use, if possible, just a single winding. And secondly, separate the turns, if possible, by 4 to 6 times the diameter of the wire, which becomes quite difficult with litz-wire, because in litz-wire the proximity effect comes twice into play. First of all, between each wire of the litz-wire itself, so this is called the internal proximity effect, and you can do nothing about that concerning separating the turns because they are just fixed, but you can at least separate the turns of the total litz-wire itself. Sounds a little bit difficult. Now, how do I come to this factor of 4 to 6? There is one very interesting graph which proves this. We'll put away the other paper. So here we can see on the x-axis we have the spacing. That's the ratio between the distance of each turn to the diameter of the wire. You can see it starts at 1, which would be turn touching turn, and 5 is 5 times the distance is 5 times the wire diameter. And here we have 7 different graphs for the number of wires or turns, and you can see if you the more turns we get, the more detrimental the effect becomes, but it tapers out. However many turns we have, if we get to at least 4 or 5, or to be 100% sure 6 times the diameter, then the effect of raising, this is here on the y-axis, is how much the additional the factor that comes in addition to the skin effect due to the proximity effect, and should be ideally 0, which would mean proximity effect gives 0 extra resistance, and all the graphs taper out near the 0 effect when we are above a ratio of distance turn to diameter of the wire, if it gets 4 or larger. So 4 to 6 times we're on the safe side. But you cannot always realize this. Depending on the kind of coil you wind, this is not always possible. So you always have to balance skin effect and proximity effect, and you only can do this with some approximations, or you take a lot of measurements, or you just use the Excel sheet I prepared to give you at least an impression and an approximate values of what's better to use litz-wire, better to use copper wire, copper tubing, what is the effect of separating the turns, etc. So that was it for today. Got to quite some length, but these are really the 2 most important effects to take into account when winding a high quality factor, high Q factor magnetic antenna coil. And there still remain 2 very important and 1 less important effects, which we will talk about next time. And these are losses due to dielectric and magnetic losses, or ferromagnetic losses. But that was it for today. So stay tuned. If you found it interesting, give it a big thumbs up. And I say bye from Roger, bye from Kinecast Labs. Until next time.